Imagine looking up and seeing a sun so enormous that it fills the sky, appearing roughly 70 times larger than our own sun does from Earth. In this world, that is ordinary. Nothing here is built to last. Metal does not cool into solid ground. It hangs in the atmosphere as vapor. Astronomers first found this planet after detecting a signal so unusual that for a moment they suspected something had gone wrong with their instruments. The world circles its star so closely that an entire year passes in little more than a day. There are no oceans, no rain, no clouds drifting overhead. The heat is so overwhelming that the molecules needed to build them are torn apart before they can survive. Even the planet itself is losing the battle. Its star is stripping away its atmosphere, carrying pieces of the world into space, one atom at a time. This is not a theoretical nightmare dreamed up by computer models. It is a real planet, confirmed by multiple observations, cataloged by astronomers, and studied with some of the most powerful telescopes ever built. The deeper scientists looked, the stranger it became, because every new measurement pushed this world farther beyond the limits of what anyone expected a planet could endure. We make these long form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe, and we'll be here whenever you need a quiet journey through the cosmos. The story begins with a simple question: how do you find a planet that no one can see? To understand this remarkable world, we first need to know what kind of place it is. It is an exoplanet. The name simply means a planet that travels around a star other than our own sun. Every one of these distant worlds circles a different source of light, often so far away that no telescope can separate the planet from the glare of its parent star. Finding one is remarkably delicate. We cannot usually see the planet itself. Instead, astronomers watch the star. If a planet passes directly between its star and us, the star grows ever so slightly dimmer for a brief time. That tiny dip in brightness is called the transit method, a technique that reveals an otherwise hidden companion through the faintest change in light. Again and again, patient observation turns these nearly invisible patterns into evidence. But the search that uncovered this particular world did not begin with the largest observatories on Earth. It began with two modest robotic telescopes created for the Kilodegree Extremely Little Telescope Survey. One watched the skies from Arizona, the other operated beneath the skies of South Africa. Together, they monitored thousands of bright stars, night after night, measuring minute variations that human eyes could never notice on their own. Among those countless points of light, one star behaved in a way that demanded closer attention. Careful follow up observations confirmed the signal, and an international team led by astronomer Scott Gowdy announced the discovery across the years 2016 and 2017. Their findings appeared in the journal Nature, placing the remarkable planet into the growing catalog of confirmed worlds beyond our solar system. Its formal designation became Kilodegree Extremely Little Telescope 9b. It is also cataloged as Hotel Delta 195,689b. The names may sound impersonal, yet they mark one of the most extraordinary planetary discoveries ever recorded. This distant world lies about 670 light years from Earth, within the constellation Cygnus, meaning the light carrying its story began its journey centuries before reaching our telescopes. Astronomers also organize stars into families according to their surface temperatures. The sequence begins with the hottest stars, followed by progressively cooler groups. Those categories are known as the O type, B type, A type, F type, G type, K type, and M type stars. Our own sun belongs to the G type family, resting comfortably near the middle of that sequence rather than its blazing upper end. Most planets discovered so far orbit cooler stars than the hottest members of that scale. But this world circles something altogether more unusual. Long before anyone understood the planet itself, the nature of its parent star was already challenging expectations in ways that few astronomers had anticipated. Before we look any closer at the planet itself, our attention settles on the star that dominates every moment of its existence. Its catalog name is Kilodegree Extremely Little Telescope 9. Like the world circling it, the name feels almost ordinary. The star is anything but. Across the growing collection of known planetary systems, very few stars resemble this one in any meaningful way. Astronomers classify stars by temperature and mass, placing them into the sequence we have already touched upon. Kilodegree Extremely Little Telescope 9 occupies the narrow boundary between the late B type class and the early A type class. That position carries enormous consequences. These stars are far hotter, brighter, and more massive than stars like our own Sun. They burn through their nuclear fuel at a tremendous pace, pouring vast amounts of energy into the surrounding space every moment of their lives. Its surface reaches approximately 10,170 Kelvin. That corresponds to about 9,897 degrees Celsius, or 17,847 degrees Fahrenheit. Our own Sun, by comparison, has a surface temperature of roughly 5,500 degrees Celsius, or 9,932 degrees Fahrenheit. The difference is staggering. We are no longer comparing ordinary variations between neighboring stars. We are looking at a furnace operating in an entirely different league. Brightness follows naturally from that heat. So does radiation. Every photon leaving this stellar surface carries the imprint of conditions far more intense than those surrounding Earth. As you imagine this distant system, it helps to remember that the planet is not orbiting a slightly warmer version of our Sun. It circles a star whose physical nature pushes well beyond the environments where astronomers once expected planets to survive. But history makes this discovery even more remarkable. Before Kilodegree Extremely Little Telescope 9 entered the astronomical record, only 6 confirmed planetary systems were known around A-type stars. None of those host stars approached the extraordinary temperatures measured here. The boundaries seemed well established, shaped by decades of observation and careful analysis. The B-type category appeared even more forbidding. Despite extensive surveys across the sky, no confirmed planet had ever been found orbiting a B-type star. The absence was striking enough that many researchers viewed it as a genuine pattern rather than simple coincidence. Stars this hot were generally considered unlikely homes for planets that could remain detectable over long periods. Then this system emerged from the data. It fit the measurements. Independent observations agreed. The evidence held together under repeated examination, even though it challenged long standing expectations. We often think scientific discovery expands familiar ideas. Occasionally, it forces those ideas to bend instead. By every expectation that came before, a planet circling a star this extreme should never have been there at all. Instead of asking how hot this world becomes, let us first consider its shape. Size alone already tells an unexpected story. When astronomers measured the planet's mass, they found a giant that outweighs Jupiter by about 2.8 times. On its own, that figure suggests a remarkably substantial world, one carrying far more material than the largest planet in our own solar system. Yet another measurement immediately complicates that picture. Its radius, the distance from its center to its outer edge, reaches nearly twice that of Jupiter. That is an astonishing amount of space for a planet with only a few times Jupiter's mass. If you could somehow place the two worlds beside one another, this distant giant would spread across a much greater volume, occupying far more room than its familiar counterpart. The numbers refuse to settle comfortably together. Greater mass usually means stronger gravity pulling material inward, producing a more compact body. We see that pattern repeated throughout many planetary systems. Larger worlds often squeeze themselves tighter under their own weight. This one follows a different path. But density reveals the real surprise. Density simply describes how much matter is packed into a given amount of space. A block of solid iron feels heavy because its matter is crowded closely together. A sponge feels light because much of its volume is empty space. When astronomers calculated this planet's density, they discovered it measured less than half that of Jupiter, even though the planet itself contains considerably more mass. That combination transforms the way we picture it. Instead of imagining a compact giant, we begin to see an enormous globe whose outer layers have expanded far beyond ordinary expectations. It remains a gas giant, yet its atmosphere stretches outward to an unusual degree, giving the planet a swollen appearance, unlike the denser worlds we know best. Many giant planets beyond our solar system show signs of inflation, the gradual expansion of their outer layers beyond what simple planetary models predict. This world belongs among the most dramatic examples ever measured. The difference is large enough that astronomers cannot dismiss it as ordinary variation or minor uncertainty in the observations. Independent measurements continue to support the same conclusion. As you follow these measurements, an important tension begins to emerge. The planet possesses enough mass to suggest a tighter structure, while its enormous radius argues for something actively pushing its atmosphere outward. Gravity continues pulling inward every moment. Another influence is clearly resisting that pull, reshaping the planet into a form that its mass alone cannot explain. For now, the mathematics leaves us with a world that appears far larger than it has any obvious reason to be. Distance changes everything. A planet may possess enormous mass, an unusual atmosphere, or an extraordinary star, yet the path it follows through space often decides the conditions that shape every moment of its existence. In this system, that path is astonishingly small. Kilodegree Extremely Little Telescope, 9b, circles its parent star at a distance of only about 0.0346, 2 astronomical units. An astronomical unit is the average distance between Earth and the Sun, making it a convenient way to compare planetary orbits. Measured against that familiar scale, this giant world travels roughly 30 times closer to its star than Earth does to ours. The gap separating planet and star is so narrow that the usual sense of planetary distance almost disappears. Picture our own solar system for a moment. Mercury already races around the Sun on an orbit far inside Earth's path, enduring intense sunlight compared with our world. Yet even Mercury remains vastly farther from its star than this planet does from Kilodegree Extremely Little Telescope 9. The comparison reminds us that we are no longer dealing with ordinary planetary arrangements. We have entered a category where proximity becomes one of the defining characteristics. But closeness also transforms the passage of time. A longer orbit requires a longer year. A shorter orbit finishes far more quickly. Because this planet circles so near its blazing star, gravity drives it around at tremendous speed. One complete journey takes less than 1.5 Earth days. Expressed another way, an entire year on this distant world lasts only about 36 hours. That rhythm is almost impossible to picture using everyday experience. Before you have finished what would feel like 2 ordinary days on Earth, this giant planet has already completed another full circuit around its star. The familiar pace of seasons loses all meaning. Any marker we associate with the passage of a planetary year is compressed into little more than the span between one evening and the next. Even the immense scale of the orbit becomes strangely intimate. The planet never spends long moving away from one side of its path before curving back toward the point where its journey began. Around and around it goes, tracing the same remarkably tight route with unwavering precision, each circuit governed by the powerful pull of the brilliant star at its center. But these measurements reveal more than speed alone. They describe a world that exists in almost constant embrace with its star, where distance has been reduced to the smallest fraction of what we know at home. Every orbit reinforces that closeness, allowing the star to dominate nearly every physical process taking place across the planet, hour after hour, year after astonishingly brief year. The pace of the orbit tells only part of the story. What truly defines this world is the extraordinary flood of energy pouring onto it every moment. Distance determines exposure, and here that relationship reaches an astonishing extreme. By combining the star's tremendous brightness with the planet's remarkably close orbit, astronomers calculate that kilo-degree extremely little telescope 9b receives roughly 44,000 times more stellar energy than Earth receives from the Sunday. That number deserves a moment of thought. It is so immense that ordinary comparisons begin to lose their meaning. Imagine standing beneath a gentle morning sky on Earth, feeling sunlight gradually warm your skin. Now imagine multiplying every ray by tens of thousands. The comparison remains imperfect, yet it hints at the overwhelming intensity arriving at this distant planet without interruption. This constant torrent reaches every layer facing the star. Light is only one part of it. The planet is immersed in an enormous stream of radiation spread across many wavelengths, each carrying energy into the atmosphere with relentless persistence. Every second brings another wave, then another. There is no meaningful pause between them, but the consequences extend far beyond warmth. On Earth, sunlight powers weather, drives winds, and supports living ecosystems. There, incoming energy can be balanced by oceans, clouds, ice, and an atmosphere that redistributes heat around the globe. None of those familiar stabilizing influences can perform the same role here. The incoming radiation overwhelms almost every ordinary planetary process before it has much chance to respond. You can picture the planet resting beneath an immense waterfall of starlight, except the falling water never slows and never spreads out. Every moment adds another layer of energy onto a world already struggling beneath the previous one. The planet is continually exposed to conditions that few other confirmed worlds are known to endure. Astronomers often describe stellar energy using careful measurements rather than dramatic language, because the mathematics already speaks clearly. A value this high is not merely an interesting statistic. It becomes the central force shaping nearly every characteristic of the planet. Its atmosphere, its chemistry, its structure, and even its long-term future are all influenced by this uninterrupted bombardment from the nearby star. But there is another step beyond the numbers themselves. Receiving such extraordinary energy is one thing. We can calculate it with confidence, using distance and brightness alone. Understanding how that energy transforms the planet requires us to look much closer at the conditions where the radiation finally arrives. There, at the surface facing its brilliant star, the physical consequences become almost beyond comparison with any world in our own solar system, revealing a level of heat that challenges the ordinary distinction between planets and stars themselves. Now the measurements arrive at the point where ordinary language begins to struggle. All the calculations of distance, brightness, and incoming radiation finally meet a single reality on the planet itself. Astronomers estimate that the side permanently facing the star reaches a temperature of roughly 4,600 Kelvin. That is about 4,300 degrees Celsius, or 7,772 degrees Fahrenheit. For a planet, the number is almost unbelievable. We are accustomed to worlds with frozen poles, scorching deserts, or thick clouds hiding warmer layers below. None of those familiar comparisons prepare us for temperatures climbing into a range more commonly associated with stellar surfaces than planetary atmospheres. The day side of this giant exists under conditions that stretch the very meaning of what a planet can endure. The comparison with our own sun makes the scale even clearer. The sun's visible surface measures roughly 5,500 degrees Celsius or 9,932 degrees Fahrenheit. This distant world's blazing dayside is only about 1,200 degrees Celsius lower. In cosmic terms, that is an astonishingly narrow gap between a planet and the star that dominates our own solar system. But another comparison may be even more surprising. Across the galaxy, countless small red dwarf stars burn at lower surface temperatures than the dayside of kilodegree extremely little telescope 9b. Those objects are genuine stars, producing energy through nuclear fusion deep within their cores. Yet when we compare only their surface temperatures, this planet's illuminated hemisphere surpasses many of them. A confirmed planet is, at least across one face, hotter than some confirmed stars. That distinction deserves careful thought. Temperature alone does not determine whether an object is a planet or a star. Stars generate their own energy through sustained nuclear fusion, while planets do not. The difference is fundamental. Even so, when a planet reaches temperatures normally reserved for stellar surfaces, our familiar categories begin to feel far less intuitive than they once did. You can almost sense the boundary becoming less obvious. The atmosphere behaves under conditions that few planetary models were ever designed to describe. Matter responds differently. Chemistry changes. Even the appearance of the world would bear little resemblance to the gas giants we know within our own solar system. But there is one important limitation. These extraordinary temperatures belong primarily to the hemisphere facing the star. The opposite side lives under very different conditions, preventing the planet as a whole from crossing into truly stellar territory. If every region of this world reached the same extraordinary heat, the distinction between planet and star would become far more difficult to picture, even though the underlying physics would still place each in its own separate class. Imagine placing one hand near a blazing fire and never being allowed to turn away. That image comes surprisingly close to the reality of this distant world. Its extraordinary heat is not shared evenly across the globe because the planet keeps the same face turned toward its star throughout every orbit. Astronomers call this state tidal locking. In simple terms, the planet rotates at exactly the same rate that it circles its star, allowing one hemisphere to face the light continuously, while the opposite hemisphere never receives direct daylight. We have already seen this behavior much closer to home. Earth's own moon is tidally locked to our planet, always presenting the same familiar face as it travels around us. The hidden side certainly receives sunlight during part of its orbit, but we never see it from Earth. Kilodegree Extremely Little Telescope 9b experiences something far more extreme. Here, the locking occurs between a giant planet and an intensely luminous star, creating a far harsher division between one hemisphere and the other. The hemisphere facing the star exists beneath uninterrupted daylight. There is no sunrise, no sunset. The brilliant star hangs in the same position forever, pouring energy onto the atmosphere without relief. Every hour resembles the one before it. Every orbit preserves the same orientation. The blazing hemisphere never receives a chance to cool beneath darkness. The opposite side follows an entirely different rhythm. It never witnesses the star climb above the horizon. Day never arrives there. Instead, that hemisphere remains in permanent night, cut off from direct stellar illumination, while the planet continues racing around its incredibly tight orbit. Although heat can still move through the atmosphere from one side to the other, the source of that heat remains fixed on only one face of the planet. But this arrangement creates more than a simple contrast between light and darkness. It establishes two neighboring worlds sharing the same planet. One hemisphere receives relentless stellar energy. The other exists beyond direct illumination. Between them lies a transition unlike anything experienced on Earth, where our rotating planet constantly redistributes daylight across every continent and ocean. You can picture the dividing region as a vast ring encircling the globe, separating endless daylight from endless night. It is neither fully one nor the other. Conditions there emerge from a continual struggle between energy arriving from the illuminated hemisphere and cooling toward the dark side. Instead of moving across the landscape as sunrise and sunset do on Earth, this boundary remains anchored in place while the atmosphere flows across it. The existence of permanent day and permanent night already makes this planet remarkable. But the boundary joining those extremes proves just as fascinating because it becomes the meeting place where two radically different environments press against one another without ever exchanging places. The picture becomes even stranger when we stop looking at the planet itself and instead trace the path it follows around its star. We often imagine planets moving along a broad level track, circling roughly above a star's equator, in much the same way that the planets of our own solar system travel around the Sunday. Kilo degree. Extremely Little Telescope 9b refuses to follow that familiar arrangement. Its orbit rises almost directly over the star's poles. Astronomers describe this as a nearly polar orbit, meaning the planet's path is tilted by roughly 85 to 88 degrees compared with the star's rotation. Instead of circling around the star's middle, the planet repeatedly sweeps from one polar region to the other, crossing an orientation that very few known giant planets have ever displayed. That geometry immediately sets this system apart. Most ultra-hot Jupiters remain much closer to the equatorial plane of their parent stars. Their orbits resemble flattened rings surrounding the stellar equator. This world follows an entirely different route, cutting across the star from a dramatically different angle. The unusual alignment changes how the planet receives energy throughout each rapid journey. But the consequences are more subtle than simply pointing in a different direction. As the planet races around its star in only about 36 hours, the changing orbital angle causes different regions of the tidally locked world to receive the greatest intensity of stellar heating at different moments during the orbit. Although one hemisphere always faces the star, the shifting geometry alters how that hemisphere is presented relative to the star's hotter and cooler regions. The result is unlike the familiar progression of seasons on Earth. During a single orbit, lasting little more than a day and a half, the planet experiences conditions that astronomers describe as two summers and two winters. These are not seasons driven by changing weather, growing vegetation, or melting ice. They arise from the changing orientation between the tilted orbit and the rapidly rotating star, producing repeated cycles of stronger and weaker heating within one astonishingly brief year. For a long time, this intricate behavior remained hidden. Earlier observations revealed the planet's unusual orbit, yet the complete seasonal pattern required a more detailed view. It was only after observations by the Transiting Exoplanet Survey satellite that astronomers confirmed this remarkable cycle. By measuring subtle changes in the system with exceptional precision, the spacecraft revealed how the planet's extraordinary orbital geometry shapes the rhythm of its changing environment. Even after everything we have already learned, this world continues to resist simple descriptions. A year lasts only hours. One face never turns away from the star, and the orbit itself carries the planet through a repeating sequence of 2 summers and 2 winters before another astonishingly brief year begins again. The remarkable orbit did not reveal itself through a photograph or a dramatic image. Instead, it emerged from tiny distortions hidden within starlight itself. Every observation began with light, leaving the star, crossing hundreds of light years of space, and finally reaching instruments sensitive enough to measure changes almost beyond imagination. The method responsible for this discovery is called Doppler tomography. The name sounds technical, yet the underlying idea is surprisingly approachable. As the planet moves across the face of its star, it temporarily blocks small portions of the rotating stellar surface. Because one side of the star rotates toward us, while the opposite side rotates away, each region produces slightly different patterns within the star's light. By following those changing patterns during the transit, astronomers can reconstruct the path the planet takes across the stellar disk. Most planetary systems produce a familiar signature. The shifting pattern moves across the star in a predictable way, reflecting an orbit aligned reasonably well with the star's rotation. Years of observations had established what that signal should resemble. Researchers knew the expected rhythm before the measurements even began. But this system refused to follow that script. As the Discovery team examined the changing pattern within the stellar light, something immediately stood apart from previous observations. The signal drifted across the star in an unexpected direction. Instead of tracing the path associated with an ordinary orbit, it carved out a geometry that seemed inconsistent with nearly every known example at the time. That unusual result demanded careful attention. Extraordinary measurements always invite caution, especially when they challenge established expectations. The researchers had to consider whether the surprising signature reflected a genuine planetary orbit or some unnoticed problem with the observations themselves. Instruments can introduce subtle errors. Data processing can create misleading patterns. Every possibility required careful examination before any conclusion could be trusted. The more the team tested the observations, the stronger the evidence became. Independent measurements continued to reproduce the same unusual behavior. The shifting pattern remained consistent, surviving every attempt to explain it away as an observational mistake. What first appeared to be an unexpected anomaly gradually transformed into one of the defining characteristics of the system. But the importance of that discovery extended beyond a single planet. The distorted signature revealed that this giant world was traveling across its star along a path unlike anything previously catalogued for such an extreme system. Without Doppler tomography, that remarkable geometry might have remained hidden behind the overwhelming brightness of the star itself. Instead, the planet announced its presence through the smallest changes in light, allowing astronomers to recognize that they were looking at an orbital arrangement far outside the patterns they had come to expect. Every unusual orbit invites the same deeper question: how did a planet end up there in the first place? The measurements can describe where kilodegree extremely little telescope 9b travels today with remarkable precision, yet they cannot replay the sequence of events that carried it into such an extraordinary arrangement. For that, astronomers must combine observations with carefully tested models of planetary formation and evolution. The complete answer remains uncertain. Several ideas continue to compete, and none has yet explained every detail of this remarkable system. But despite those remaining questions, many researchers agree on one important point. This giant planet almost certainly did not begin its existence where we find it today. Current models suggest that giant planets form much farther from their parent stars. In those colder outer regions of a young planetary system, large amounts of gas and icy material can gather around growing planetary cores. The environment is far more favorable for building enormous worlds than the fiercely heated region close to a brilliant star. By that reasoning, a massive gas giant orbiting almost against the stellar surface appears difficult to explain if it had always remained there. Instead, astronomers believe many ultra-hot Jupiters spend part of their lives migrating inward. Migration simply means that a planet changes its orbit over time, rather than remaining where it originally formed. This gradual movement can occur through interactions with the surrounding disk of gas during the system's youth, through close encounters with other planets, or through the gravitational influence of distant stellar companions. Different systems may follow different paths. But kilodegree extremely little telescope 9b appears to carry evidence of a particularly unsettled past. Its sharply tilted orbit does not resemble the orderly architecture expected from a calm evolutionary history. Rather than circling neatly along the same general plane as its parent star's rotation, the planet travels on a path that hints at powerful gravitational disturbances somewhere along its journey. You can think of the orbit as a lasting record of earlier events. Just as layers of rock preserve traces of ancient landscapes on Earth, orbital geometry can preserve clues about encounters that happened millions of years ago. Those encounters may no longer be visible, yet their influence remains written into the planet's motion around its star. Researchers sometimes describe this kind of orbit as a fingerprint left by dynamical evolution, meaning a history shaped by changing gravitational forces instead of remaining stable from the beginning. The exact sequence of events may never be reconstructed in complete detail. Even so, the evidence points toward a world whose path through space was altered repeatedly before settling into the remarkable orbit we observe today. Rather than drifting peacefully into place, this planet appears to have reached its present home through a far more turbulent history, carrying the marks of that long journey every time it circles its extraordinary star. While the planet carries the marks of a turbulent past, the star itself refuses to remain still. Many stars rotate steadily over long periods, yet kilodegree extremely little telescope 9 spins with astonishing speed. Its rotation is roughly 38 times faster than that of our own Sun, placing it among the more rapidly rotating stars known to host a confirmed planet. The difference becomes easier to appreciate when we compare a single rotation. Our Sun requires about 27 Earth days to complete one turn on its axis. Kilodegree, extremely little telescope, 9 finishes the same journey in only about 16 hours. Before a single Earth day has passed, the star has already spun completely around, carrying its immense surface through another full rotation. Such speed changes the star itself. Gravity constantly pulls stellar material toward the center, while rapid rotation pushes outward most strongly around the equator. The two effects compete continuously. As the star spins faster and faster, the outward force slightly stretches the equatorial region while the poles remain comparatively compressed. The result is a star that is not a perfect sphere. Instead, it becomes gently flattened, with a broader middle and slightly shortened polar regions. But the shape is only part of the story. The changing strength of gravity across the stellar surface also changes its temperature. Astronomers call this effect gravity darkening. In simple terms, regions where gravity pulls more strongly become hotter and brighter, while regions where gravity is weaker become somewhat cooler and less luminous. The star develops an uneven surface, with its poles radiating more intensely than its equator. That uneven brightness leaves a measurable signature. As the planet passes in front of the star, it does not block light from a surface that shines equally everywhere. Instead, it crosses regions of different brightness and temperature. The resulting transit appears slightly lopsided, producing subtle irregularities within the recorded light that could not be explained by an ordinary, uniformly glowing star. For a time, those irregularities puzzled astronomers. The observations remained consistent, yet straightforward models failed to reproduce what the telescopes were recording. The planet itself could not account for every detail. Something about the star had to be influencing the measurements in a fundamental way. The answer emerged only after researchers incorporated the star's extraordinary rotation into their calculations. Once the flattened shape and gravity darkening were included, the asymmetric transit finally made sense. The pieces fit together naturally. Rather than introducing confusion, the rapid spin became the missing explanation, linking the observations to the physical reality of this remarkable system. Even before we examine the planet's atmosphere, the star has already demonstrated that it is an active participant in every measurement astronomers make, shaping the light long before that light ever reaches Earth. Age often changes the way we understand a star. Some shine steadily for billions of years before entering more dramatic stages of evolution. Others race through their existence far more quickly, burning their fuel at an extraordinary rate. Kilodegree Extremely Little Telescope 9 belongs to that second group. Although it already appears immensely powerful, astronomers estimate that it is only about 300 million years old, making it remarkably young by stellar standards. That figure may sound immense from a human perspective. Civilizations rise and disappear in only thousands of years, while mountains slowly change over millions. Yet stars live on vastly different timescales. Our own sun is about 4,600,000,000 years old and still rests comfortably within the stable portion of its life. Compared with that familiar benchmark, the star before us has existed for only a small fraction of the time. Its youth carries important consequences for the planet circling it. We sometimes imagine harsh environments developing gradually as stars grow older and more unstable. Here, the evidence points in another direction. The intense radiation, the overwhelming heat, and the relentless stellar energy are not recent developments in the history of this system. They have defined it from almost the very beginning. As soon as the young giant planet settled into its present orbit, it entered an environment already dominated by an exceptionally luminous star. Every orbit completed since then has unfolded beneath that same extraordinary brilliance. Every layer of its atmosphere has evolved under conditions unlike those experienced by the giant planets of our own solar system. But youth also means tremendous vigor. Massive stars consume their nuclear fuel far more rapidly than smaller stars because they generate energy at astonishing rates. They blaze brilliantly, yet they pay for that brilliance with shorter lifetimes. Kilodegree Extremely Little Telescope 9 is still in one of the earlier chapters of its existence, already releasing immense amounts of energy while possessing much of its stellar future ahead of it. For the planet, that future offers little relief. It has not endured millions of years waiting for the star to become more hostile. Hostility has always been the normal state of its surroundings. The world has never known a gentler sky, a cooler era, or a more forgiving parent star. From its earliest formation until the present moment, every rotation and every remarkably brief year have unfolded beneath the same relentless conditions. When we picture this distant system, it helps to remember that we are not witnessing a temporary episode. We are seeing the environment in which this planet has spent essentially its entire existence, shaped from the beginning by a young, exceptionally powerful star whose influence reaches into every part of the world that circles it. Heat changes matter in stages. We have already crossed beyond the familiar ones. Long before rock begins to soften or metals begin to glow, another transformation takes command. At temperatures like these, the very bonds holding atoms together inside molecules can no longer endure. The process is called molecular dissociation, meaning complete molecules are torn apart into their individual atoms by overwhelming thermal energy. This is not a rare event on the day side of this world. It is the normal condition. Every moment, enormous amounts of energy pour into the atmosphere from the nearby star, striking gases with such intensity that stable molecular structures continually come apart. Instead of remaining linked together, atoms separate and drift independently until conditions allow them to combine once again. Hydrogen offers the clearest example. Under ordinary circumstances, hydrogen usually exists as molecular hydrogen, meaning two hydrogen atoms joined together as a single molecule. Here, that familiar arrangement cannot survive for long. The fierce heat breaks molecular hydrogen into atomic hydrogen, leaving countless individual hydrogen atoms suspended throughout the upper atmosphere. But hydrogen is only the beginning. The same conditions affect many of the molecules we normally associate with planetary atmospheres. Water cannot remain intact. Carbon dioxide cannot maintain its chemical structure. Methane faces the same fate. Their atoms are pulled apart almost as quickly as they have any opportunity to combine, preventing these familiar compounds from becoming lasting features across the blazing hemisphere. That realization changes the way we picture this planet. We often imagine atmospheres as collections of recognizable gases interacting through weather and circulation. Here, the atmosphere behaves more like an enormous chemical battlefield. Molecules constantly form where conditions briefly permit, only to be dismantled again beneath the relentless flood of stellar energy. Construction and destruction proceed together without lasting balance. You might expect chemistry to become simpler under such extreme conditions. Instead, it becomes remarkably dynamic. Every collision between atoms carries the possibility of creating something new, while every surge of heat threatens to undo it moments later. Stability becomes temporary, transformation becomes continuous. But this relentless cycle extends beyond chemistry alone. The atmosphere itself changes character because the particles moving through it are no longer the same ones found in cooler giant planets. Instead of drifting through layers dominated by ordinary molecular gases, energy passes through a mixture increasingly filled with isolated atoms created by constant molecular breakup. We have now arrived at a place where even the basic building blocks of an atmosphere struggle to remain assembled. The familiar chemistry that shapes worlds across much of the galaxy cannot keep pace with the extraordinary conditions surrounding this remarkable planet. Under such relentless radiation and astonishing heat, matter itself is continually rewritten, one broken molecular bond at a time. Instead of asking what gases fill this atmosphere, we have to ask a different question altogether. Which atoms remain standing after such relentless heat has stripped ordinary molecules apart? The answer reshapes everything we normally expect from a giant planet. Once familiar compounds disappear, the atmosphere must rely on an entirely different collection of particles to interact with passing light. Astronomers describe this interaction using the word opacity. Opacity simply means how easily light can pass through a material, or how strongly that material absorbs and blocks it. On many planets, molecules such as water or carbon dioxide provide much of that filtering. They leave recognizable patterns within the starlight crossing the atmosphere, allowing researchers to identify their presence from unimaginable distances. But those dependable molecular fingerprints have largely vanished here. With the dayside continually dismantling complex molecules into individual atoms, light encounters a very different environment. Instead of flowing through layers dominated by molecular gases, it passes through an atmosphere increasingly shaped by isolated atoms that absorb specific colors of light in their own distinctive ways. Among the most influential of those atoms are metals. Under ordinary conditions, we think of metals as solid materials locked inside rocks or planetary interiors. Here they exist in gaseous form because the surrounding temperatures are high enough to free individual atoms into the atmosphere itself. They drift through the blazing skies, not as droplets or dust, but as separate atomic particles suspended within the scorching gas. That difference gives this world an unexpected resemblance. Rather than behaving like the atmosphere surrounding a conventional giant planet, its upper layers begin to resemble the outer regions of a relatively cool star. There, too, atoms play a dominant role in shaping the light that eventually reaches distant telescopes. The comparison does not erase the distinction between planet and star, yet it draws the two categories surprisingly close under these extraordinary conditions. But resemblance does not mean identity. The immense mass needed to ignite sustained nuclear fusion, the process that powers true stars by combining lighter atomic nuclei into heavier ones while releasing vast amounts of energy, remains absent. This world still depends entirely upon its nearby star for the relentless energy transforming its atmosphere. Even so, the chemistry visible above its dayside often appears strikingly stellar. For you, that means every observation becomes an exercise in reading atomic signatures instead of molecular ones. Researchers no longer search primarily for familiar compounds. They examine delicate patterns left behind by individual atoms, each absorbing its own narrow range of light, while revealing another piece of this extraordinary atmosphere. Those patterns become a catalog of elemental survivors, showing exactly which metals endure where ordinary planetary chemistry can no longer persist. Evidence soon followed the theory. As increasingly sensitive observations examined the atmosphere in greater detail, researchers found exactly the kind of atomic signatures that such an extraordinary environment should produce. Their measurements transformed an unusual prediction into a confirmed reality, revealing that this atmosphere contains materials rarely encountered in planetary skies. In 2018, an international research team from the University of Geneva and the University of Bern announced a remarkable discovery. By studying the faint fingerprints left within starlight passing through the atmosphere, they directly detected neutral atomic iron, ionized atomic iron, and ionized titanium. Neutral atoms still retain all of their electrons. Ionized atoms have lost one or more electrons after absorbing enough energy, becoming electrically charged. Both forms were present, demonstrating just how intensely the surrounding radiation reshapes the atmosphere. The finding carried enormous significance. Scientists had previously observed iron in many places across the universe, including stars and vast clouds between them. They also expected iron to exist deep inside giant planets, hidden within rocky material, or combined with other compounds. But this marked the first confirmed detection of iron existing as a gas within the atmosphere of any known planet. That statement deserves a moment of reflection. Iron is one of the substances we instinctively associate with strength and permanence. We build bridges from it. Mountains contain it. Planetary cores are rich with it. Yet on this remarkable world, temperatures are so extreme that iron does not remain locked inside minerals or dust. Individual atoms drift freely through the atmosphere, carried by fierce currents, instead of resting inside solid rock. But the discovery also explained why ordinary expectations no longer apply here. On cooler giant planets, iron usually becomes trapped within molecules or condenses into tiny particles that settle deeper into the atmosphere. Those familiar pathways cannot persist beneath this relentless heating. Before iron has an opportunity to hide inside more stable chemical structures, the surrounding energy tears those structures apart, leaving exposed atomic iron suspended high above the planet. Ionized titanium told a similar story. Its presence confirmed that the atmosphere is energetic enough to strip electrons away from heavy elements, creating conditions that resemble those found around stars more than traditional planetary environments. Each detected atom became another piece of evidence, showing that we are observing chemistry operating under extraordinary physical extremes. You can almost imagine the atmosphere as an immense laboratory where familiar elements behave according to unfamiliar rules. Iron remains visible because nothing cooler can shelter it. Every observation strengthens the same remarkable conclusion. This is a world where substances we normally expect to find inside rocks have become part of the sky itself. The first detections were only the beginning. As observational techniques improved and astronomers gathered increasingly detailed spectra, the atmosphere revealed itself as something even more extraordinary. Each new examination uncovered additional atomic fingerprints, suggesting that this remarkable world held a far richer chemical inventory than anyone had first imagined. Follow-up spectroscopy, the study of how matter absorbs and emits different colors of light, expanded the picture dramatically. Every chemical element interacts with light in its own unique way, leaving an unmistakable signature within the spectrum recorded by a telescope. By comparing those delicate patterns with laboratory measurements on Earth, researchers could identify individual elements from hundreds of light years away. Using the Global Architecture of Planetary Systems program, together with the high-accuracy radial velocity planet searcher, North Spectrograph, scientists steadily added new members to the growing list. They detected calcium, magnesium, sodium, chromium, scandium, and yttrium within the atmosphere. Even more remarkably, several of these elements appeared in both neutral and ionized forms, showing that the relentless heat and radiation continually push atoms between different energetic states. Each detection carried its own importance. Together, they painted an entirely new portrait. Instead of an atmosphere dominated by familiar planetary gases, we were looking at an environment where numerous metallic elements drifted freely as individual atoms, suspended high above the planet beneath conditions almost unimaginable elsewhere. The atmosphere had become a vast collection of elemental signatures, each one visible because the surrounding temperatures refused to let more complex chemistry endure. But what truly stands out is the sheer variety. On most planets, many of these elements remain hidden inside rocks, condensed minerals, or microscopic dust particles. Here they are exposed directly to observation. Rather than disappearing beneath clouds or becoming trapped within solid material, they remain aloft as vaporized atoms, each leaving its own narrow imprint across the incoming starlight. Imagine looking upward on such a world. You would not find a sky defined by the chemistry familiar to Earth or even to the giant planets of our own solar system. Instead, every beam of light passing through the atmosphere would carry the spectral fingerprints of nearly a dozen metallic elements, revealing a place where the heavens themselves are filled with vaporized metals instead of ordinary molecular gases. For you, this changes the meaning of an atmosphere. We usually picture air as something transparent and chemically familiar. On this distant planet, the sky has become an immense archive of atomic physics. Every observation uncovers another elemental survivor, preserved within a furnace that continuously strips matter back toward its simplest forms while allowing those enduring metallic atoms to announce their presence across the gulf between worlds. Far above the atmosphere we have explored so far, another boundary comes into view. It cannot be seen through a telescope, and no spacecraft could fly across it and watch a line appear beneath its instruments. Yet this invisible frontier determines whether a planet keeps its atmosphere or gradually surrenders it to space. Astronomers call this boundary the Roche lobe. The name describes the region around a celestial body where its own gravity remains strong enough to hold material close. You can picture it as the outcome of an endless tug of war. On one side, the planet pulls its gases inward. On the other, the nearby star exerts an even greater attraction. Somewhere between those competing forces lies a delicate dividing line. Beyond that limit, the star begins to win. For most planets, this boundary sits comfortably beyond the atmosphere itself. Their gases remain securely contained, circulating above the surface without constantly threatening to escape. But this world lives under conditions unlike those of almost any other known giant planet. The tremendous heating has caused its hydrogen envelope to swell outward until it stretches astonishingly close to that gravitational frontier. That detail carries enormous consequences. The atmosphere is no longer resting safely within the planet's grasp. Instead, its outermost layers press against the very edge of what gravity can retain. Every energetic hydrogen atom, climbing higher into the atmosphere, moves through a region where the balance between escape and confinement becomes increasingly fragile. But gravity never stops competing. The nearby star continually pulls at those expanded upper layers, encouraging the highest portions of the atmosphere to drift farther from the planet. At the same time, the planet struggles to draw them back. Neither influence disappears. They remain locked together, shaping the atmosphere from moment to moment through an unending gravitational contest. You can think of the upper atmosphere as standing on a narrow ridge between possession and loss. A slight increase in energy gives individual atoms a better chance of crossing the invisible boundary. A slight decrease allows gravity to reclaim them. The outcome depends upon countless microscopic motions unfolding across an atmosphere already transformed by extraordinary heat. This reveals another consequence of living so close to such a powerful star. The atmosphere is not merely heated until its chemistry becomes unfamiliar. It has expanded so dramatically that it now strains against the limits of the planet's own gravitational reach. The giant world still holds itself together, yet its outer hydrogen envelope exists in a remarkably precarious state, lingering near the point where the star's relentless pull can begin carrying pieces of the atmosphere away into the surrounding darkness. Time allows changes that no single observation can reveal. A planet may appear unchanged from one year to the next, yet over immense spans, it can surrender astonishing amounts of itself. For this world, that slow transformation has finally been measured rather than imagined. In the year 2020, researchers calculated the rate at which the atmosphere escapes into surrounding space. Their analysis showed that the planet is losing material equal to somewhere between 18 and 68 Earth masses during every 1 billion years. Those numbers describe a process unfolding without interruption, driven by relentless heating and the constant pull of the nearby star. At first, such a timescale feels almost impossible to grasp. A billion years stretches far beyond human history, civilizations, or even many familiar landscapes on Earth. But the measurement gives us something remarkable. We are no longer speaking only about a hostile atmosphere or powerful radiation. We are witnessing a planet that can no longer keep everything it was born with. Imagine watching a mountain lose a single grain of sand every moment. Nothing appears different after one glance. Return after another glance, and the mountain still seems complete. Yet enough time changes the picture entirely. The same principle applies here, although the scale rises beyond anything found within our own planetary experience. But the escaping material is not measured in scattered particles alone. Added together across cosmic time, the loss becomes comparable to entire worlds. Dozens of Earth's worth of mass gradually drift away, carried from the swollen outer atmosphere into interplanetary space. The process remains continuous, unfolding hour after hour, year after year, without requiring dramatic explosions or catastrophic impacts. Gravity still resists this escape. The planet continues pulling inward while the star draws outward. Heat gives atoms additional energy, lifting them toward the fragile boundary we have already crossed together. Some return. Others continue climbing until the planet can no longer reclaim them. From that point onward, they become part of the surrounding stellar environment rather than part of the planet itself. You and I naturally think of planets as enduring objects, changing only through rare disasters, but this giant challenges that expectation. Its transformation is steady instead of sudden. Each moment removes only a minute fraction of its total mass, yet the accumulated effect across hundreds of millions and billions of years becomes extraordinary. The result is a world engaged in a prolonged surrender. It still circles its brilliant star with remarkable speed. It still possesses an immense atmosphere rich with extraordinary chemistry. Yet, even as it continues its orbit, part of that atmosphere slips away forever, leaving the planet incrementally lighter than it was before, one unbroken moment after another across the vast calendar of the universe. Some forms of light carry consequences far beyond illumination. As we continue across this remarkable world, we find that one particular band of stellar radiation shapes the fate of the entire atmosphere. It arrives unseen, yet its effects reach from the uppermost layers of gas to the edge of space itself. The driving force is called extreme ultraviolet radiation. In simple terms, this is an especially energetic form of ultraviolet light, carrying enough energy to strip electrons from atoms and heat the highest parts of an atmosphere with extraordinary efficiency. Measurements indicate that this planet receives roughly 700 times the extreme ultraviolet radiation experienced by the previously studied class of hot Jupiters. That difference changes everything. Heat alone cannot fully explain what we observe, but this intense radiation continuously pours energy into the outer atmosphere, where hydrogen atoms gain enough speed to challenge the planet's gravitational hold. Instead of remaining bound, increasing numbers climb higher, reaching the fragile limit where escape becomes possible. The atmosphere expands further, becomes thinner, and loses still more material as the process continues without pause. You can picture it as a constant transfer of energy rather than a single violent event. Every moment, fresh radiation arrives from the nearby star. Every moment, hydrogen atoms respond. Some remain trapped after collisions with neighboring particles. Others acquire just enough energy to continue outward, crossing the invisible threshold beyond which the planet can no longer reclaim them. The result is a continuous atmospheric wind flowing into surrounding space. But researchers believe the story may extend even farther from the planet itself. Several scientific studies have proposed that the escaping hydrogen could stretch behind the world, forming an enormous stream of evaporating material. In broad concept, such a structure would resemble the tail of a comet, except its source would not be melting ice. Instead, the tail would consist of atmospheric gas gradually carried away under the combined influence of radiation and stellar gravity. That possibility remains an active area of research. Current observations suggest the idea is physically plausible, and theoretical models support the formation of such an extended cloud under conditions this extreme. Yet astronomers continue gathering evidence before treating it as firmly established. Additional observations across different wavelengths of light will help determine whether such a tail truly exists and how large it might become. Even without a confirmed tail, the underlying process stands among the most intense examples ever measured around a giant planet. We are watching a world exposed to radiation so powerful that its atmosphere cannot remain entirely its own. The star supplies the energy, hydrogen answers the call, and the gradual escape continues across immense spans of time, leaving behind a planet that changes through persistence rather than sudden catastrophe. New observations have carried the story even farther. For years, hydrogen seemed to be the principal witness to this extraordinary escape. But fresh evidence revealed that the atmosphere is surrendering far more than its lightest ingredient. The loss reaches deeper into the planet's chemical makeup. In the year 2025, a study using the Hubble Space Telescope reported one of the clearest signs yet that heavier material is also leaving this remarkable world. Researchers detected ionized magnesium and ionized iron extending beyond the planet's Roche lobe. As we explored earlier, that invisible boundary marks the region where the star's gravitational pull begins to overcome the planet's ability to retain its own atmosphere. Finding these metals beyond that limit provides direct evidence that they are escaping into surrounding space. This discovery carries enormous significance. Hydrogen is the lightest element in the universe, so astronomers have long expected it to escape more readily from intensely heated planets. Metals tell a different story. Iron and magnesium possess far greater mass, making them much more difficult to accelerate, to escape speeds under ordinary conditions. Yet around this world, the radiation environment has become so extreme that even these heavier atoms are carried outward with the expanding atmospheric flow. But the finding also connects beautifully with everything we have already uncovered. Earlier observations revealed vaporized metals suspended throughout the atmosphere, existing as individual atoms because familiar molecules cannot survive such overwhelming temperatures. Now we see that at least some of those same metallic elements are no longer confined to the planet at all. They are crossing the gravitational frontier, and becoming part of the surrounding stellar environment. You can almost picture the atmosphere unfolding layer by layer. Hydrogen races outward first, driven by intense extreme ultraviolet radiation. Mixed within that flow are heavier particles, pulled along by the same expanding stream until some of them also pass beyond the point of return. The escape is no longer limited to the lightest gases. It reaches into material that once seemed securely bound within the planet's upper atmosphere. Scientists continue refining their understanding of exactly how efficiently these heavier elements are transported away, and many details remain under active investigation. Even so, the overall picture has grown much clearer. This giant world is losing more than an envelope of gas. It may also be surrendering portions of the very metallic elements whose spectral fingerprints first revealed such an extraordinary atmosphere. The result is a planet that changes in composition as well as mass. Every successful observation uncovers another layer of that transformation, showing us a world whose identity is gradually being carried away into space, atom by atom, under the relentless influence of its brilliant neighboring star. Even now, this extraordinary world continues revealing new secrets. Long after its blistering temperatures, escaping atmosphere, and metallic chemistry first astonished astronomers, another observation opened an entirely new window into what is happening above the planet. The story has not reached its ending. It is still unfolding with each generation of instruments pointed toward this distant system. In the year 2026, astronomers using the Keck planet finder reported the detection of hydrogen airglow rising from the day side of Kelt 9b. Airglow is the faint natural light produced high in an atmosphere when atoms absorb energy and later release part of it as visible light. Earth experiences the same phenomenon in its own upper atmosphere, although ours is vastly gentler. On this distant planet, the process unfolds under conditions unlike anything found within our solar system. The signal itself proved especially remarkable. Rather than appearing as a single smooth feature, the emitted light formed a distinctive double-peaked pattern. That unusual shape carried far more information than a simple detection alone. By examining the precise form of those peaks, researchers could directly investigate the temperature of the escaping gas, estimate its density, and measure how powerful atmospheric winds move through the expanding hydrogen envelope in real time. What had once been inferred indirectly could now be observed with far greater confidence. But this discovery represents more than another entry in a growing catalog of observations. It changes the way astronomers can study atmospheric escape itself. Earlier measurements relied mainly on material passing in front of the star during transit, revealing what the escaping atmosphere absorbed from starlight. Airglow approaches the problem from another direction. Instead of watching the atmosphere block light, we detect the atmosphere producing a faint glow of its own. That difference helps untangle long-standing uncertainties about the structure and motion of the escaping gas. You can almost imagine the upper atmosphere announcing its presence across the darkness. Excited hydrogen atoms release tiny flashes of light before continuing their outward journey, leaving behind a spectral fingerprint that sensitive instruments can recognize across immense distances. Those photons carry the history of the atmosphere's motion, revealing winds, heating, and expansion in ways that were previously hidden from view. But perhaps the most striking realization is how recent this achievement truly is. We are not looking back at a discovery from decades ago. We are witnessing one of the newest exoplanet findings on record, made while this field of astronomy continues advancing at extraordinary speed. Every fresh observation adds another layer to a world that refuses to become familiar, reminding us that even after everything we have learned, Kelt 9b continues to surprise the people studying it. Perspective changes everything. After spending so long inside the extraordinary conditions surrounding Kelt 9b, it helps to step back and place this world among the other remarkable planets astronomers have discovered. Only then does its true position become unmistakable. We are not comparing it with ordinary planets anymore. We are comparing it with the harshest planetary environments ever measured. Before Kelt 9b entered the scientific record, the title of hottest known exoplanet belonged to WASP 33b. That planet circles an intensely hot star and reaches temperatures that already stretch the limits of familiar planetary physics. For years, it represented the upper boundary of what researchers believed a gas giant atmosphere could endure. But the discovery of Kelt 9b forced scientists to redraw that boundary. Its dayside temperatures rose far beyond those earlier expectations, creating physical conditions that pushed planetary science into new territory. But Kelt 109b does not stand alone. It belongs to a remarkable family known as ultra-hot Jupiters. This name describes giant gas planets orbiting so close to their stars that their atmospheres experience extraordinary heating. Within this group, every member offers a different lesson about how matter behaves under relentless radiation. Each one reveals another piece of the puzzle. Together they form a natural laboratory unlike any found in our own solar system. Consider WASP 76b, where observations suggest iron may condense into droplets on the cooler hemisphere after existing as vapor on the intensely heated dayside. The image of iron rain captured worldwide attention, yet the underlying science reflects the remarkable temperatures that separate ordinary weather from chemistry rarely seen elsewhere. But even that famous world remains cooler than Kelt 9b, whose dayside heat prevents many familiar molecules from surviving long enough to participate in comparable cycles. Then there is WASP 12b, another giant planet orbiting exceptionally close to its star. Its atmosphere also reaches temperatures capable of vaporizing metallic materials, while intense tidal forces distort the planet itself and contribute to the loss of atmospheric matter into surrounding space. Those characteristics established it as one of the most extreme planets ever examined, yet measurements continue placing Kelt 9b beyond even those extraordinary conditions. The distinction matters because it rests upon observation rather than dramatic language. Researchers compare temperatures, stellar radiation, atmospheric chemistry, escaping material, and spectroscopic measurements collected across many years. Each comparison points toward the same conclusion. Kelt 9b occupies the furthest known edge of this already astonishing planetary class. But that title carries deeper meaning than simply being the hottest. It represents the current limit of measured planetary endurance. Every new ultra-hot Jupiter discovered is weighed against this remarkable benchmark, and each comparison reminds us that Kelt 9b remains the most extreme member of an already extraordinary family of worlds. Earlier in our journey, we encountered a puzzle that seemed almost too strange to accept. Kelt 9b appeared unusually swollen for a planet with so much mass. Its outer layers stretched farther into space than simple size estimates first suggested. At the time, the reason remained incomplete. Now, enough pieces have come together for that picture to sharpen. The explanation begins with heat itself. Every gas responds to rising temperature by expanding as its particles move faster and push farther apart. You have seen this principle on Earth in everyday materials, although usually on a much smaller scale. On Kelt 9b, the same physical law operates without restraint. Under relentless stellar energy, the upper atmosphere swells outward until an entire planetary envelope becomes dramatically enlarged. But this expansion changes more than appearance. As the atmosphere spreads across a greater volume, its average density falls. The same amount of material becomes distributed through a much larger region. Gravity still reaches outward from the planet's enormous mass, yet it must hold on to gas that now occupies a far broader space. The atmosphere becomes more extended, more fragile, and increasingly vulnerable to outside forces. This is why astronomers describe Kelt 9b as inflated. The planet itself has not become a giant solid object growing beyond its original boundaries. Instead, its gaseous exterior has expanded under extraordinary heating until the outer layers no longer resemble the compact atmospheres surrounding cooler giant planets. The change is physical, measurable, and consistent with the extreme environment created by its nearby star. But expansion carries an unavoidable consequence. Gas that drifts farther from the planet's center experiences a weaker gravitational grip than gas closer below. Every additional layer, lifted outward, moves nearer the delicate balance where the star's gravity and intense radiation begin exerting greater influence. Material that might have remained secure under cooler conditions now occupies a region where escape becomes increasingly possible. The different discoveries we have followed begin fitting together with remarkable consistency. The broken molecules, the extended hydrogen envelope, the vaporized metals, and the measured streams of escaping material all describe different expressions of the same underlying process. Extreme heating first reshapes the atmosphere, then prepares it for gradual removal. One phenomenon naturally supports the next. But the radiation pouring from the star completes the sequence. An atmosphere that has already expanded becomes far easier to erode than one packed tightly against the planet. Energetic light reaches into those elevated layers, driving atoms beyond the planet's gravitational hold and carrying them into surrounding space. Inflation, therefore, serves as more than an interesting characteristic. It becomes one of the central reasons Kelt 9b continues losing part of itself, its enlarged atmosphere offering less resistance as the long process of planetary erosion steadily unfolds across cosmic time. Time eventually changes every star, even one that now appears overwhelmingly powerful. The fierce brilliance surrounding Kelt 9b belongs to a stage that, remarkable as it seems, will not last forever. Stellar evolution continues whether planets survive it or not, carrying both worlds toward a future that astronomers can model, even if they cannot describe every detail with certainty. Current studies suggest that within roughly 200 million to 300 million years, Kelt 9 will begin moving toward the giant branch of stellar evolution. This phase marks a major transformation in a star's lifetime. After exhausting the hydrogen fuel within its central core, the balance between gravity pulling inward and energy pushing outward begins to shift. The star responds by expanding dramatically while its internal structure rearranges into a new configuration. But that expansion changes the entire architecture of the planetary system. A star growing larger does not simply occupy more space. Its increasing size, changing radiation, and evolving gravitational environment reshape the conditions experienced by every nearby companion. For a planet already orbiting at an extraordinarily small distance, even modest outward growth becomes profoundly important. Kelt 9b occupies precisely that vulnerable position. Its orbit lies so close to the star that astronomers expect the expanding stellar surface to move progressively nearer over time. As the star continues entering this later stage of its existence, present calculations indicate that its outer layers are likely to encroach upon the region where the planet now travels. The separation that currently exists may gradually disappear as stellar evolution unfolds across millions of years. That possibility naturally raises another question. What happens when those boundaries finally meet? Here, the scientific picture becomes much less certain. Researchers do not describe a single confirmed ending for Kelt 9b. Instead, they discuss several physically plausible outcomes, each depending upon details that remain difficult to predict with complete confidence over such immense spans of time. But uncertainty does not mean ignorance. Astronomers understand the governing physics remarkably well, even while recognizing that complex interactions between stellar expansion, atmospheric escape, orbital evolution, and tidal forces could influence one another in ways that alter the planet's final path. Small differences accumulating across hundreds of millions of years may ultimately determine whether the world gradually spirals inward, loses much of its remaining atmosphere before direct contact, or experiences another sequence that existing models have not yet resolved completely. For now, Kelt 9b remains a living laboratory rather than a completed story. We can trace the direction of its future with increasing confidence, yet the final chapter still resists certainty. That restraint is important. The planet's long-term outlook appears increasingly challenging as its star grows older, but scientists continue describing its ultimate fate as an open question, shaped by evidence, guided by theory, and awaiting discoveries that future observations may someday provide. Some worlds confront a single danger. Kelt 9b exists beneath several at once. Each process unfolds on its own timescale, yet all of them overlap across the same extraordinary planet. When we gather every discovery together, the result is neither a simple catastrophe nor a single dramatic event. It is a layered story of continuous survival under conditions unlike any other confirmed planetary environment. Closest to the star, relentless radiation pours into the atmosphere without pause. Energetic light tears apart familiar molecules until individual atoms dominate the upper layers. Those atoms absorb more incoming energy, expanding the atmosphere farther into surrounding space. Material reaches heights where the planet's gravitational hold grows weaker, allowing hydrogen and even heavier elements to begin slipping away. None of these changes happen in isolation. Each one strengthens the next. But the atmosphere does not disappear all at once. It is reduced gradually, atom after atom, year after year, across spans of time that dwarf human history. Measurements collected through spectroscopy reveal this slow erosion as an observable physical process rather than an abstract prediction. We are watching a planet lose part of itself, while it continues circling the same brilliant star that drives the loss. Far beyond these immediate changes lies another chapter written on a much longer clock. Kelt 9 itself will eventually leave its present stage of stellar evolution and expand as its internal structure changes. Current models indicate that this future transformation could bring the growing star into the region occupied by the planet's orbit, although the precise outcome remains uncertain. That possibility belongs to the distant future, while atmospheric escape is occurring today. Yet one detail stands apart from the rest. Despite the extraordinary punishment already measured, Kelt 9b appears massive enough to avoid complete evaporation during the remaining stable lifetime of its host star. The ongoing loss is substantial, but present scientific models indicate that the planet is unlikely to vanish entirely before the star begins its own dramatic evolution. It continues to endure beneath conditions that would overwhelm far less massive worlds. But endurance should not be mistaken for safety. Every orbit carries another dose of extreme radiation. Every passing age removes more material from the atmosphere. Every stage of stellar evolution gradually reshapes the future awaiting the system. Survival, in this case, is not the absence of damage. Survival is the ability to remain despite damage that never truly stops. As we look upon Kelt 9b now, you are not seeing a world frozen in a single moment. You are witnessing an object caught inside several overlapping stories at once, each progressing at its own pace. One strips away atoms, another transforms the parent star across millions of years. Together they reveal a remarkable truth. Even under permanent siege, some worlds continue existing, carrying the visible marks of every force that has tried and continues trying to undo them. When we step back from individual measurements and discoveries, Kelt 9b begins to resemble something larger than an extraordinary planet. It becomes a reminder that the universe writes many different histories. The path that produced Earth, with long periods of relative stability and conditions that allowed complexity to flourish, represents only one outcome among countless possibilities. As you travel farther into the galaxy with us, that realization grows harder to ignore. Planet formation often begins in similar ways, inside broad disks of gas and dust surrounding young stars. Tiny grains collide, larger bodies emerge. Gravity gathers material into worlds. Yet, those shared beginnings do not guarantee similar endings. Slight differences in timing, mass, neighboring planets, or the behavior of the host star can redirect an entire planetary future. From those small changes, vastly different destinies unfold. But Kelt 9b appears to have experienced a particularly turbulent history. Earlier evidence points toward migration, the gradual movement of a planet from one orbit to another through powerful gravitational interactions within its planetary system. Rather than remaining where it first assembled, this giant world likely traveled inward until it reached the fierce environment we know today. Every stage of that journey would have altered the conditions surrounding it. That migration was more than a change of location. It reshaped everything that followed. A planet forming farther from its star could preserve very different atmospheric properties than one born close to intense radiation. Once that world drifted inward, familiar physical processes began operating under unfamiliar extremes. Heat transformed chemistry. Radiation accelerated atmospheric escape. Gravity struggled against expanding gases. Each chapter emerged naturally from the one before. We sometimes imagine planets as permanent destinations, fixed in place from the beginning of time. Nature offers a more dynamic picture. Worlds can move, orbits can change, stars evolve. Entire systems continue adjusting long after their earliest moments have passed. Stability exists, yet so does continual transformation, and both belong to the same universe. But there is no need to describe this history as tragic. The planet has followed the physical rules governing its surroundings from the moment it formed. Its present condition reflects those rules acting over immense spans of time, each influence leaving another visible mark. We are not witnessing a failure of planetary evolution. We are witnessing one valid outcome among many allowed by the laws of nature. Perhaps that is the deeper perspective Kelt 9b offers. When you compare it with the familiar world beneath your feet, the contrast feels astonishing. Yet both planets emerged from the same cosmic ingredients. Both obey gravity, chemistry, and the flow of stellar energy. Their differences reveal how flexible those shared beginnings can become. Across the galaxy, there is no single script for a planet's life. There are countless variations, each shaped by its own history, each carrying the imprint of the journey that brought it there. Against that broader backdrop, our own planet comes into sharper focus through comparison rather than celebration. Earth occupies a rocky orbit around an ordinary, middle aged star, whose energy output has remained comparatively steady across immense stretches of time. That stability has never meant complete stillness. Continents shifted, climates changed, and life repeatedly adapted. Yet the larger framework surrounding those changes remained remarkably consistent. We often overlook how many circumstances must align before such continuity becomes possible. A planet must circle at a distance where temperatures allow liquid water to persist across long periods. Its atmosphere must retain enough gas to moderate surface conditions without becoming overwhelmingly dense. The host star must avoid overwhelming instability while providing dependable energy year after year. Each factor influences the others, creating a balance that can endure for extraordinary spans of time. But the growing catalog of planets beyond our solar system reveals how uncommon that particular combination appears to be. Astronomers have now confirmed several thousand worlds around distant stars, representing an astonishing range of environments. Many orbit so closely that their years last only a handful of days. Others travel around faint red stars, massive blue stars, aging giants, or pairs of suns moving together through space. Some appear covered by deep global oceans. Others may consist largely of rock, ice, or enormous envelopes of gas. Every new discovery expands the possibilities. Several planets occupy regions where radiation shapes their atmospheres far more aggressively than it shapes ours. Others follow elongated paths that expose them to dramatic swings in stellar heating. Some appear tidally locked, always presenting the same hemisphere toward their star, creating permanent dayside and nightside conditions unlike anything experienced on Earth. Each system demonstrates another solution produced by gravity, chemistry, and time. But no single characteristic determines whether a planet resembles our own. Distance alone cannot explain it. Neither can planetary size, atmospheric composition, or the age of the host star when considered separately. Those properties interact continuously, producing environments that often surprise the scientists studying them. As more observations accumulate, familiar expectations continue giving way to greater diversity. You can almost sense astronomy adjusting alongside the evidence. Early expectations often imagined distant planetary systems reflecting our own arrangement with only minor differences. Modern observations tell a richer story. Planetary systems vary enormously, and each new detection adds another example that broadens our understanding of what nature can assemble. Seen from that perspective, Earth appears neither typical nor impossible. It represents one outcome within an immense population whose members have followed very different paths. Celt 9b illustrates one extreme. Countless others occupy positions somewhere between those distant limits. Together they remind us that planetary history is shaped by countless interconnected circumstances, and among the worlds discovered so far, the combination of orbital distance, stellar character, and atmospheric balance that defines our home has appeared far less often than many once expected. The remarkable picture we now hold did not appear all at once. It emerged gradually, assembled across many years through patient observation by different telescopes, different research teams, and different generations of scientists. Each instrument contributed only part of the story. One measured the planet's orbit, another revealed traces within its atmosphere. Later observations refined those findings, adding depth where earlier studies had offered only outlines. No single observatory carried this discovery alone. Small ground based telescopes first revealed that an unusual world existed. The Hubble Space Telescope added crucial evidence about its escaping atmosphere. The transiting exoplanet survey satellite improved measurements of the planet's motion across its star, helping astronomers refine its physical properties. More recently, observations from the Keck Observatory uncovered additional details about atmospheric behavior that earlier instruments could not resolve. Each contribution depended upon the ones that came before, turning isolated measurements into a coherent portrait. But what makes this process extraordinary is the nature of the evidence itself. We have never photographed mountains on this distant world. We have never crossed its atmosphere or placed a spacecraft into orbit around it. Everything we know has been inferred from light, the faint stream of information traveling across approximately 670 light years before finally reaching our telescopes. That means the photons entering those instruments began their journey roughly 670 years ago, long before modern astronomy existed. Light carries remarkable detail. As that light passes through the planet's atmosphere, certain wavelengths become slightly weaker because specific atoms absorb them. Spectroscopy, the study of how light is divided into its individual colors, allows scientists to recognize those missing patterns like fingerprints. Tiny shifts within the same signals reveal motion through the Doppler effect, meaning changes in wavelength caused by movement toward or away from us. From those delicate variations, researchers estimate wind speeds, atmospheric structure, orbital motion, temperature, and chemical composition. But none of those conclusions rests upon a single observation. Confidence grows because independent measurements repeatedly support one another. Separate instruments, observing at different times and often for different purposes, gradually reinforce the same physical picture. The result resembles a mosaic assembled piece by piece until the larger image becomes unmistakable. Across more than a decade, scattered measurements became one of the most detailed studies ever constructed for a planet humanity will almost certainly never visit. The world itself remains unimaginably distant, yet the light arriving from it has allowed us to reconstruct its chemistry, its escaping atmosphere, its winds, and the graceful mechanics of its orbit. Across centuries of travel, those ancient photons carried enough information to make an unseen world feel astonishingly real. As our journey reaches its natural resting point, Kelt 9b feels less like an impossible curiosity and more like a place that exists according to the same physical laws shaping every corner of the cosmos. Its fierce environment does not stand apart from nature. It belongs within it. The same gravity that guides Earth's orbit holds this distant planet near its brilliant star. The same atoms found throughout the universe drift through its atmosphere, even under conditions unlike anything we have ever experienced. That perspective changes the way we see it. Along the way, we have traced the planet's migration through its early history, followed the expansion of its atmosphere beneath relentless radiation, watched individual atoms escape into space, and examined the observations that revealed metals suspended high above its clouds. We have seen how different telescopes, operating across many years, gradually transformed scattered measurements into a coherent understanding. Even its distant future remains part of that picture, described carefully through evidence rather than certainty. But Kelt 9b is neither a warning nor a spectacle. It is simply one honest data point within an astonishingly varied universe. Among thousands of known planets, it occupies one extreme. Elsewhere, astronomers continue finding frozen worlds, rocky worlds, gas giants, ocean candidates, and systems unlike any imagined before they were discovered. Each new observation widens the range of what planetary evolution can produce. Perhaps that is why this world remains so compelling. Its value does not come from breaking records alone. It comes from revealing how flexible nature can be when familiar processes unfold under unfamiliar conditions. The chemistry, the atmospheric escape, the shifting winds, and the changing orbit all follow understandable physics. Together, they create a planet that once seemed unimaginable, yet now feels increasingly knowable. Even now, the picture remains incomplete. Recent observations, including the detection of hydrogen air glow during 2026, demonstrate that this world continues offering fresh information to anyone patient enough to collect its ancient light. Each improvement in technology allows scientists to ask more detailed questions, and sometimes the answers reveal entirely new layers that earlier generations could not have measured. The story grows through careful accumulation rather than sudden revelation. You and we are living during a remarkable period for planetary science. New worlds continue appearing in astronomical catalogs, while familiar ones continue revealing unexpected details. Kelt 9b will almost certainly change again as future observations refine today's conclusions or uncover phenomena that remain hidden within existing data. That possibility does not diminish what we know. It strengthens it, because science remains willing to improve its understanding whenever better evidence arrives. Across the immense distance separating us from this remarkable planet, the light continues traveling, and with every new observation, another small piece of its story reaches us.